morning, good afternoon, and good evening. Thank you for joining us today. My name is Allie Kane, and I will be the moderator of our presentation. I'm part of Fluor's Office of Technology, which focuses on using science and innovative engineering technology to build a better world. Our engineers, designers, and experts, our people, are at the core of our success. Today's webinar is intended for managers of owner-operator companies with facilities that require industrial water usage. Today, subject matter expert Tamim Popalzai will talk about achieving greater water sustainability through minimum liquid discharge, or MLD. Tamim will compare MLD with other traditional approaches such as zero liquid discharge or business as usual, aka no water recovery, and discuss why MLD can be beneficial for clients from both an economic and an environmental standpoint. So let's meet our speakers. First, we have Tamim Popalzai, one of Fluor's water subject matter experts. Tamim has over 21 years of experience in the design and operation of industrial water and wastewater treatment systems in a wide range of industries. He has a diverse background with experience in various phases of project development, including feasibility, detailed design, project management, startup and commissioning, and troubleshooting. Tamim holds a master's degree in civil and environmental engineering from Norwich University in Vermont. He loves volleyball, water sports, and spending time with his family. And then for today's health, safety, and environmental topic, which sets the stage for our webinar today, I'd like to introduce Himanshu Dey. Himanshu is a chartered chemical engineer in the UK with more than 30 years of experience in all spheres of the upstream oil and gas industry, including oil and gas processing and produced water treatment for injection and disposal. He has worked on the design and commissioning of produced water treatment systems, as well as debottlenecking of existing systems with Fluor, as well as with other companies throughout his career. Himanshu likes reading, walking, and traveling. He particularly enjoys history, mainly the early to Middle Ages. All right, and with that, I'd like to hand it over to Himanshu and get us started for today's presentation.
Thank you, Ellie. Today's HSE topic is global water risk, its likelihood and impact. Since 2009, global leaders in business, academia, government, and NGOs have met to identify and discuss the most pressing global business risks. The World Economic Forum has repeatedly identified the water supply crisis as the top 5 global risks in terms of likelihood and impact since 2012. Water crisis is defined by World Economic Forum as a significant decline in the available quality and quantity of fresh water, resulting in harmful effects on human health and/or economic activity. The graph in the presentation shows the various risks identified in different categories. It is clear that the water crisis is quite significant both in terms of impact as well as likelihood. Due to the combination of population growth, unsustainable water withdrawals, and poor governance, insufficient water supply has become a reality in many parts of the world. As can be noted from the water stress map on the screen, businesses are directly impacted by limited resources across various regions. Now, what is water stress? Water stress measures the ratio of total water withdrawals to available water supplies, both surface and groundwater. Water withdrawals include domestic, industrial, and agricultural uses. Higher values indicate more competition among the users. With the global energy demand on course to rise by 2040, that will also increase the energy sector's water consumption by approximately 60%. Therefore, for existing and future projects, we should be developing answers to the following questions. Is there water stress in the vicinity of my project in the near term or in the future life of the project? What are the alternative ways my project can reduce the amount of water consumption? What are the water reuse opportunities for my project? What are the life cycle cost impacts for importing water from various sources? What is the current and future water regulatory landscape that may impact my project's water demands? And how can I implement water reuse in my current facility? Now over to Tamim for today's main topic.
Thanks, Himanshu. To all attendees, hello, and thank you for taking the time to join today and listen in. Himanshu's water stress topic is a great segue into the subject that I'd like to address, which is achieving water sustainability through minimum liquid discharge. Since water scarcity is an established risk for the majority of the countries and water demand is forecasted to significantly increase through all major industries, it is essential that businesses optimize their water consumption and learn about water savings and water recovery options. This is where minimum liquid discharge strategies come in. MLD provides one of the most efficient options for water recovery. MLD is more effective and less complex than traditional zero liquid discharge thermal systems. And more importantly, it puts less stress on the environment, making it more sustainable. The initial focus of this presentation will be outlining what MLD is and why MLD should be considered. Secondly, the discussion will present a few treatment strategies and technologies for achieving MLD. A further section will discuss the costs associated with a typical MLD plant. And finally, a case study is presented to describe and compare MLD with other traditional approaches such as ZLD or business as usual, no water recovery. With this key information, we hope that you'll gain a reasonable understanding of why achieving sustainability with minimum liquid discharge makes sense both for economics and environmental sustainability. I'd like to start this presentation by defining water sustainability as the ability to meet the water needs of the present without compromising the ability of future generations to do the same. Now, achieving water sustainability is important for the following reasons. First, water scarcity is now a reality in many parts of the world, and for most, sustainable water reuse is not considered an option any longer, but a necessity. Second, throughout the globe, environmental regulations for discharge are getting more stringent, requiring robust treatment, such as California's Code of Regulation and EPA's National Pollutant Discharge Elimination System. Third, water sourcing and water disposal costs are on the rise. Factors such as water quality, transport distance, and volume of water impact the pricing. Water stress states such as California are constantly revising unit costs for importing water from various sources. Fourth, newly developed technologies are designed with sustainability in mind and provide higher water recovery at lower costs and energy consumption. Fifth, reusing water reduces the overall water footprint, putting less stress on the local water resources, such as local aquifers that are typically used for potable water. And finally, many corporations are implementing water sustainability initiatives that include water conservation and reuse. So by understanding these risk factors, Fluor seeks to help clients advance their water sustainability initiatives by incorporating MLD strategies to ensure project success and promote sustainable development and building a better future. Now let us start by defining the term minimum liquid discharge, which is typically defined as a core set of proven technologies and processes that enable users to recover 95 to 99% of the liquid waste streams that may be otherwise wasted. Now, as you well know, water treatment systems produce a waste or a reject stream during the treatment process, which contains a certain level of contaminants. Such a waste stream can be anywhere from 25 to 50% of the total water supplied to the treatment system. This liquid waste stream represents a substantial loss of potential valuable resource. Minimizing this waste stream is one of the ways to solve a part of the water crisis and an opportunity for reuse to optimize a plant's life cycle cost. How does MLD compare to traditional ZLD treatment systems? Let us first define ZLD, which is a water treatment process in which all of a facility's liquid waste is purified, recycled, and therefore leaves zero discharge at the end of the treatment cycle. At the same time, it produces solids from the liquid stream, which may be recovered in some cases or disposed. A typical ZLD system can include process technologies such as ultrafiltration, reverse osmosis, and most typically evaporators and crystallizers. MLD can technically recover up to 99% of the liquid waste streams from brackish water treatment plants. However, there is a limit of how much water can be recovered based on a facility's water chemistry, and in particular, the total dissolved solids. MLD systems have a maximum TDS concentration limit of 260,000 milligrams per liter based on current membrane-based technologies. This leaves 1 to 5% of the volume as a brine stream, which can be discharged to an evaporation pond, an injection well, an outfall discharge source, or sent to a brine sewer line, depending on the salinity and the volume of the stream. As for a ZLD system, treating this remaining 5% of brine volume typically makes it cost prohibitive, unless there's a mandatory requirement of no liquid discharge from a facility. To summarize, MLD is a recommended water recovery strategy over ZLD, as it uses a more familiar membrane treatment process that is less complex than thermal systems and can achieve similar water recoveries at a much lower cost. This graph is from a 2008 American Waterworks Association article that talked about ZLD technologies for inland desalination. Added to the original figure are relative recoveries and salinity levels that can be reached with today's latest membrane technologies. Based on the TDS levels shown in this example, by incorporating a MLD membrane technology, such as counterflow or osmotically assisted RO, it is possible to recover up to 97% of the feed water by increasing the brine concentration limit up to 250,000 milligrams per liter, whereas traditionally, the limit for seawater reverse osmosis systems was approximately 80,000 milligrams per liter due to the pressure limitations of the membranes. The final 5% of liquid elimination for a thermally driven ZLD system is extremely expensive with a high energy demand, and also requires exotic metallurgy to prevent corrosion at high temperatures, which it operates. Also, as can be noted, water quality, especially salinity, plays a vital role in determining the amount of water that can be recovered and concentrated. Next, we'll look into some considerations when identifying a source of water for a facility's water treatment plant, which will also enhance the efficiency of the MLD portion of the plant. Alternative water sources should be considered during project planning in order to secure a sustainable water supply for the life of a project without negatively impacting the local environment. This map shows the maximum observed TDS, total dissolved solids concentrations, in the US for shallow well water. The blue region of the map for the eastern US show TDS concentrations to be less than 500 milligrams per liter. The central and Midwest regions have a TDS in the range of 500 to 3,000 milligrams per liter, as shown in green and yellow. Some regions, such as North and Central Texas, TDS can be as high as 3,000 to 10,000 milligrams per liter for shallow groundwater. And on the Western US regions, the TDS ranges from anywhere from 1,000 milligrams per liter all the way up to 35,000 milligrams per liter. Freshwater sources, as shown in blue and green, are generally designated for potable water through stricter regulations. Industries can evaluate alternative sources of water that can meet their needs. Surface water is another important source that can be considered, and the TDS levels are expected to be comparable to the ones depicted on the map. Domestic and industrial effluent are becoming more available as a viable source, and coastal areas can consider seawater if other sources are restricted. In coastal areas, such as South Florida, saltwater intrusion can increase groundwater TDS over time. So these types of risks shall be considered closely in the planning phase of projects when evaluating different water sources. Some key considerations for identifying a water source for a project can be enumerated as follows. First, availability. The project's water source should satisfy the total water demand for the current and future phases of the project. As an example, seasonal variations of water supply and drought are currently impacting California's water supply and availability for industrial users. Second, the water quality may change over time or during seasons, and therefore it is critical to understand the variability of water quality for a particular water source. Water quality variability from water sources may include risks such as red tide, algal blooms, saltwater intrusion, and others. Third, the environmental impact. Two different sources can have varying levels of environmental impact. For example, withdrawing groundwater will eventually impact the local community's potable water supply. And even water quality versus sourcing water from a local river, which may not be as critical. Next, regulations. Several states such as California and Arizona have adopted strict regulations and policies regarding water withdrawal and discharge from industrial facilities. So it is essential to evaluate the regulatory landscape in sourcing a water supply and anticipate potential changes to water regulations. Treatability. Water sources with lower salinity, lower organics, and less suspended solids are always preferred, as it will reduce complexity, costs, and improve water recovery rates for MLD system. And finally, cost and energy. Evaluating all the above screening considerations for our MLD plant will enable a cost-effective design as well as an energy-efficient system and reduce the overall project technical and financial risks. This slide presents some of the water quality challenges when designing an MLD system, and the items of concern revolve around three categories, namely salinity, scaling, and fouling components. The figure on the left shows a typical total dissolved solids expected from liquid waste streams in a variety of industries. The most common range of salinity concentrations are highlighted in orange. The important point to note from this table is that as TDS increases, water recovery is more limited, water chemistry becomes more challenging to treat, and higher energy is required. On the top right, the table highlights some scaling compounds of concern, which greatly impact technology selection, cost, and operation of MLD systems. Scaling of reverse osmosis membranes may occur when sparingly soluble salts are concentrated within the element beyond their solubility limit. For example, if a reverse osmosis plant is operated at 50% recovery, the concentration in the reject stream will almost double the concentration in the feed stream. As the recovery of the plant is increased, so is the risk of scaling and fouling. Some of the more potent scaling compounds are from calcium and silica, as highlighted in orange in the table on the top right. To minimize precipitation and scaling, it is important to establish a well-designed scale control measure, such as anti-scalant dosing or selective ion separation technologies, such as softening, ion exchange, and nanofiltration, to limit exceeding the solubility limits. The table on the bottom right emphasizes organic and biological fouling constituents that are of primary concern. Brine liquid waste streams that have higher concentrations of BOD, biological oxygen demand, or COD, chemical oxygen demand, will require appropriate pretreatment to mitigate biological fouling of the MLD systems. Traditionally, several factors limited the overall efficiency of a membrane system. Factors such as pressure, recovery, scaling, and fouling. As will be discussed in the next section, new membrane technologies are pushing the limits of conventional reverse osmosis systems by balancing the overall pressure, preventing scale deposition by various methods, thereby allowing operation at higher recovery. This figure shows the capex on the right and the opex on the left relative to the salinity concentration. As the salinity of the water stream increases, the treatment process becomes more rigorous and expensive. As an example, traditional membrane systems shown in gray were able to reach around 8% salinity. However, with the advent of advanced membrane technologies, such as counterflow RO or osmotically assisted RO, and high-pressure membranes, ultra-high pressure membranes, the salinity envelope has reached up to 25% salinity as shown in the red box. These newer membrane-based technologies can replace traditional thermal evaporators because it requires less energy and cost to achieve similar water recovery. By understanding the project drivers and the limit of environmental constraints, we can better understand and make decisions about how to optimize the water treatment system and identify opportunities to recover water. In this diagram, you can see the fate of treated water as it passes through an industrial facility. Once the water is treated, it is passed through the utility system and eventually used in the plant process. Wastewater is therefore generated as it contacts the process and is sent to the wastewater treatment unit. When it comes to reuse, the cooling tower blowdown and the reverse osmosis reject, as shown in the orange dashed lines, are usually the place where water can be recovered. Other opportunities for reuse include the effluent from the wastewater treatment unit, which should be sent to the raw water treatment system for further processing before reuse. In this section, I'd like to introduce some thoughts regarding the latest process technology for MLD and some potential strategies that can be considered in incorporating these technologies for your facility. The graph in this slide presents traditional technologies considered for liquid waste volume reduction. The black and gray bars represent the least innovative technologies, which include evaporation ponds, evaporators, crystallizers, which are capable to achieve dissolved salt concentrations beyond 250,000 milligrams per liter and produce solids. However, more innovative membrane technologies, shown in the red box, such as CFRO and OARO, are being used in place of conventional brine concentration methods. As can be noted from the figure, new RO technologies can operate beyond 150,000 milligrams per liter with less energy, and this is the area we'd like to focus on our attention to in this presentation. This curve shows the relative maturity and level of development of desalination and brine concentration technologies over time. Now, as we all know, it takes time to develop commercial technology, particularly when there are many possible applications in a wide range of feed water salinities, compositions, and complexities. This can increase the time it takes to bring clarity to performance capabilities, cost estimates, and definition of suitable markets. From this perspective, it is not surprising that some technologies have had limited success thus far. Companies like Desaltech, Gradient, Hyrec, and Saltworks are good candidates for MLD due to their technological maturity and higher water recovery capabilities with reasonable energy consumption. The table on the right presents some recognized technologies in the brine concentration market with typical ranges for feed TDS and maximum TDS. As you can see, some of the vendors are able to achieve brine concentrations of up to 250,000 milligrams per liter. We will look a bit closer at these two technologies for MLD in the upcoming slides. Here, we'd like to note the differences between traditional RO technology compared to counterflow RO or forward osmosis. Each type uses a different technique of dealing with the osmotic pressure differential across the membrane to produce fresh water. Gradient Corporation and Hyrec each have systems known as CFRO and OARO that maintain saline solutions on both the feed and the permeate side of an RO membrane, thereby reducing the osmotic pressure difference between each side. This essentially means that high salinity feeds can be treated at the hydraulic pressure, which never exceeds 1000 psi, approximately 70 bar, which enables the use of commercially available equipment. To attain higher recovery, brine is cascaded through multiple stages. Each type of reverse osmosis system shown above can be used in conjunction with one another in order to increase the overall system recovery. In typical industrial facilities, the cooling tower blowdown and the brackish water reverse osmosis brine can be sent to a high recovery MLD system. The MLD system will recover up to 95% of the volume and produce a brine stream that can be sent to an evaporation pond, surface discharge, injection well, or brine sewer as shown in the figure. If the cooling tower blowdown has a high level of silica or organic foulants, it can be routed back to the lime softening step as shown in the dark blue dashed line. Cooling tower makeup is typically UF filtered water. However, if there are certain limitations on water chemistry, brackish water permeate can be used or blended to the filtered water, as shown in the light blue dashed line. Next, we'll discuss what type of viable technologies can potentially serve as the MLD system. Here we present two established and mature technologies that can be considered for recovering liquid waste streams from a facility. On the left is OARO, osmotically assisted RO technology. And this essentially uses two feed streams. The first feed stream is the same as the RO feed stream, processed through the membranes, and leaves the module with an increased concentration. Some of this concentrated RO stream is then recycled back to the opposite side of the membrane as a second feed stream. It is diluted through the membranes and leaves the module with decreased concentration. This reduced osmotic pressure difference between the feed and the permeate side allows the treatment of ultrasaline feeds at pressures as low as 70 bar. This also implies that OARO's maximum recovery is not limited by the burst pressure of standard RO membranes. On the right is CFRO, counterflow reverse osmosis. In the CFRO process, similarly, a dilute saline solution is introduced to the product side of the membrane to reduce the osmotic pressure barrier, thereby reducing the required feed pressure. Brine is cascaded through the multiple CFRO stages, concentrating it to the saturation for disposal or crystallization while producing a purified product stream for beneficial reuse. CFRO systems are capable of concentrating salts in the brine stream of up to 260,000 milligrams per liter while maintaining pressures under 1,000 psi or 70 bar. Counterflow RO is significantly more energy efficient than other brine recovery systems due to the ability to have multi-stage counterflow cascade. The next slide, the chart highlights the energy requirement based on salinity of the liquid stream. As the salinity of the liquid stream increases towards the right of the x-axis, the energy intensity is increased. On the top right of the graph are traditional evaporators and crystallizers that require huge amounts of energy, between 25 to 60 kilowatt hour per cubic meter. CFRO and OARO brine recovery technologies, on the other hand, can treat the same high salinity liquid streams at a fraction of the energy, at approximately 10 kilowatt hour per cubic meter, as shown in the red circle. So to sum up the technology selection for MLD, it is important to remember the benefits along with the challenges when evaluating MLD technologies. Some of the benefits can be enumerated as follows. The technology maturity and relevant references. Ultra high pressure RO, CFRO, and OARO are mature technologies with established project references operating at various chemistries and high salinities. More water recovery. MLD technologies reduce the source water consumption and increase recovery. Environmental sustainability. Technology selection should have minimal environmental impact in terms of generating the least waste and requiring the least amount of energy. Optimize life cycle cost. It is important to watch out for the items that heavily impact life cycle costs, such as the capacity of the MLD system, energy consumption, membrane replacement, and chemical usage. And finally, for the benefits, discharge regulations, we need to ensure that the MLD technology selected is capable of meeting the current and future regulations regarding water withdrawal and discharge. So what are some of the limitations of the MLD technologies? So the first one is the MLD brine stream that needs to be managed considering one of the following ways: evaporation ponds, injection wells, outfall to a local water body, or a small crystallizer if discharge is not allowed, or it could be sent to a brine sewer line. These need to be confirmed with the local regulations for your project. Another limitation for MLD technologies is the issue of fouling and scaling. Higher TDS and COD will impact fouling and scaling of membrane-based technologies. So we need to make sure to ensure that low fouling membranes are considered, and adequate pretreatment is employed to reduce and mitigate fouling and scaling. Cleaning frequency, chemical consumption, membrane warranties, replacement rates are very important items that designers and operators need to consider when selecting MLD technologies. And finally, newer technologies need a wider range of applications and lessons learned in terms of operation and maintenance, which can be leveraged across various industrial sectors. Now, I'd like to shift the focus and talk about the economics of MLD. In this section, we'll provide an overview of the published data on MLD costs. As you may recall the slide from earlier, it highlights the cost variance between MLD and ZLD with respect to salinity and water recovery. While ZLD can typically treat all of a plant's excess water streams, the cost to carry that out can vary between $15 to $25 per 1,000 gallons, or $4 to $6.50 per cubic meter, and even much higher than that when considering the overall thermal energy requirements of evaporating the water. MLD, meanwhile, does not need a thermal-based technology and can achieve greater than 95% recovery at more than half the overall cost of ZLD, in the range between $3.78 to $13.23 per 1,000 gallons, which is equivalent to $1 to $3.50 per cubic meter. The cost is therefore a direct function of processing volume, water quality, and the number of treatment steps considered in the MLD system. Let us look at an example to explore further. This slide is a summary of a pilot test conducted by Saltworks on cooling tower blowdown from a power plant. The water is first treated by primary RO, RO1, which achieves approximately 80% recovery, which was then processed at increasing recovery in 3 additional steps to obtain higher volume reduction. Each recovery stage is summarized in the table above, showing the BRINE TDS, the volume reduction, and the water recovery and the technology used. The total cost for all treatment steps for this blowdown treatment application with high silica is around $17 per 1,000 gallons, or equivalent $4.50 per cubic meter, but could be half as much as less depending on the specific site water chemistry, the amount of volume reduction desired, and the type of MLD technology used. It is important to know where to stop regarding the volume reduction. If a brine disposal option is available cheaper than a certain level of treatment, then further assessment should be made to determine the overall life cycle cost and environmental impacts. Also, capacity matters. For small capacity plants, adding unit operations can add process and operational complexities. Therefore, keeping it simple with the minimum amount of treatment steps is always recommended. Simple bench test or pilot test can considerably reduce the project risk and potentially save additional treatment steps, thereby reducing the overall life cycle costs. So to summarize the economics of MLD in published literature, MLD costs vary in proportion to the salinity and water quality and the amount of volume reduction that is required. MLD typically costs in the range of $3.78 to $13.10 per 1,000 gallons, equivalent to $1 to $3.50 per cubic meter. And technology selection, the number of treatment steps and the type of membrane used has a considerable impact on the overall costs. And some important points to note, as we mentioned, fouling and scaling of the MLD system need to be mitigated with sufficient pretreatment steps. Energy costs, local power delivery costs have a significant impact on the life cycle costs. So those need to be considered as well. And finally, chemical consumption is an important aspect of MLD systems, and the delivery costs and availability should be considered and evaluated in each project. So the next section, we'd like to present a hypothetical case study that was developed using Fluor internal data of looking at different MLD options. In this case study, we looked at 4 options for brine water disposal, options A through D. The treatment plant is designed to produce water for cooling tower makeup, utility water, and demineralized water. Option A is no water recovery. The brine generated from the plant is sent to a disposal to a municipality, sewer, with an associated disposal cost. Option B is minimum liquid discharge. It recovers 95% of the cooling tower blowdown and the RO reject and leaves a 5% brine stream, which is disposed to a brine sewer. Option C is zero liquid discharge, ZLD, and it recovers all the brine and disposes solids to a landfill. And option D is the same as option B, minimum liquid discharge. However, the only difference is that we're only treating 75% of the liquid streams of the cooling tower blowdown and RO reject, and that leaves a greater amount of water brine to dispose to the sewer. And the water source for all the options considered are secondary treated effluent from a local wastewater treatment plant, which has a TDS of approximately 1,500 milligrams per liter, silica of 1.5 milligrams per liter, and TSS of less than 10 milligrams per liter. Also, effluent from the plant's wastewater treatment is recovered in option B, C, and D and sent to the raw water treatment for further processing. Option A is business as usual, no water recovery from the plant. All liquid waste streams are sent to discharge to a municipal sewer with an associated fee. Next slide is option B, minimum liquid discharge, which we said recovers 95% of the brine stream and 5% of the brine stream is sent to a brine sewer. This MLD system considers a counterflow RO system, reverse osmosis system. Option C is the traditional zero liquid discharge to recover 100% of the liquid waste streams and has a solid stream that will be sent offsite for disposal. Technology considered for this ZLD system are evaporators and crystallizers. And option D is the same as option B, minimum liquid discharge. However, as mentioned, the difference is that it aims to recover 75% of the liquid waste streams from the plant and 25% shall be disposed to an off-site evaporation pond. So this table summarizes the overall capacities for each option and the resulting water savings. The whole plant is designed to produce 1 million gallons per day of demineralized water. Now, option A, no recovery, does not recover any liquid waste streams from the plant and will need to obtain all the raw water externally. The total amount of water recovery for option B and option C are quite significant at 3 million gallons per day. If a plant is purchasing raw water, you can note that this will be a huge cost saving over the life of the plant. Note that between the 4 cases, water savings between option B and option C are most similar because the MLD system operates at a high recovery based on this plant's particular water chemistry. The limitation for no recovery option A is that large amount of treatable water is discharged off-site that could negatively impact the environment and has an associated disposal cost. The ZLD system limitations are high CapEx and OpEx, complex operation, and high maintenance. MLD options have the limitation of discharging a small volume of brine stream. Maintenance from scaling and fouling of the MLD system is a limitation that needs further close attention. And finally, this chart presents a life cycle cost comparison for the 4 options over a period of 15 years. The assumptions are highlighted in the notes above the graph. As you can see, the green line on the graph is the ZLD option with a life cycle cost of $206 million over 15 years. $94 million for the MLD option in orange, and $88 million for the no recovery option in blue, and $68 million for a 75% MLD system. The ZLD system cost is extremely high because the capex for an evaporator and crystallizer is almost 2 times as high as other options, and the OPEX is up to 7 times as much. The no recovery option is $6 million less than the MLD option. However, this is within the plus or minus 10% margin of error for this case study. So the MLD option could be optimized further with a more detailed costing analysis. And the 75% MLD option yields the lowest life cycle cost for this case study and is considered the preferred option for this project. So what are some of the key takeaways and summary of this presentation? First and foremost, water scarcity is now a reality, and sustainable water reuse is a necessity for most owners. MLD is a more cost-effective and less energy-intensive process than ZLD. Newer membrane technologies have exceeded previous threshold limits for scaling and pressure, which allow for higher water recovery. Counterflow RO and osmotically assisted RO are some good examples of new membrane technologies that have great potential for MLD applications. Calcium and silica scaling and biofouling pose operational challenges and need to have sufficient pretreatment in order to mitigate the impact on operation of the plant. The amount of water recovery from liquid waste streams is primarily dependent on site-specific water chemistry and the type of technology considered. MLD is an effective strategy to implement sustainable water reuse with life cycle costs in the range of $3.78 to $13 per thousand gallons, equivalent to $1 to $3.50 per cubic meter. Fluor will help your project achieve sustainable water recovery by evaluating effective strategies such as minimum liquid discharge as presented here, and we look forward to hearing from you to discuss water savings opportunities for your project. And with this, I hand it back over to Ali.
Thanks so much, Tamim. All right, well, it looks like we have a couple questions that come in. And just a reminder to everyone, please, if you do have questions, you can enter them in the Q&A box and Tamim will be happy to answer. All right, so the first question that's come in, are the MLD technologies that were proposed mature technologies, and do they have project references?
So yeah, a mature technology basically is something that's been used long enough, basically defined as it's some technology has been used long enough such that its initial faults and inherent problems have been removed. So the technologies presented in this presentation are mature technologies in the sense that they are building on reverse osmosis concepts, which have been around for a very long time. And some of the vendors obviously need to develop more references due to the company age and size and the global footprint. But in general, yes, the technologies presented here, I would consider them as mature technologies.
Great, thanks, Tamim. All right, next one. How is scaling and fouling mitigated when operating at higher recoveries for a membrane-based MLD technology?
Oh, that's a great question. As highlighted in the presentation, one of the limitations of membrane-based applications is that the ions in the brine stream are concentrated by a factor which is relative to the recovery rate. So one of the best ways to mitigate the scaling and fouling is understanding the components in the feed stream and then using pretreatment steps to control those items. So pretreatment steps typically considered to control scale and fouling are softening, ion exchange, anti-scaling dosing, could be pH control, nanofiltration, and those are some examples of pretreatment steps that can help mitigate scaling and fouling.
Thanks, super informative. So what are some of the operation and maintenance requirements for the MLD technologies that you mentioned, I think ARO and CFRO?
Right, so this is an important factor in terms of operation and maintenance, is that it's a membrane-based system, and obviously the first important thing is to monitor system performance, in particular membrane pressure, flux, water quality, and flow. Those are important parameters that need to be monitored closely. And then secondly, membrane cleanings needs to be scheduled based on the indicators of performance I mentioned above. So membrane replacements are also important. Typically, MLD vendors will have membrane replacement warranties, which are prorated. So those three things I think will be able to provide good operation maintenance requirements for MLD system.
Great. Now, are there cases where ZLD becomes more cost efficient? And if so, could you give an example?
Typically, ZLD, CAPEX, and OPEX are much higher than MLD, as discussed, and it makes it difficult to compete in terms of costs. There may be certain cases where a ZLD may be cheaper. It may be in conditions where there is excess steam available, for example, or the solids that are generated from the ZLD system can be sold as a product. And then the zero liquid discharge is mandatory in some cases. So in those particular cases, they may be equivalent to MLD, but I would say in general, the ZLD costs are much, much higher than MLD.
Great, thanks, Tamim. Well, it looks like that wraps up the questions we have. We haven't had any new ones come in, so we'll go ahead and wrap up for today. Thanks so much, Tamim, for the time you've spent in preparation, and thanks to our audience for attending today. Just so you know, please continue to stay informed of our next webinars. Our next one will be on building information modeling data support for the project life cycle with a focus on construction. You can stay informed of our events by visiting the Innovation Builders page on fluor.com or following our social media channels using #InnovationBuilders. If you'd like us to send you email notifications of future webinars, please email us at innovationbuilders@fluor.com with opt-in the subject line. We appreciate your attention and thank you for dialing in today. We'll send out a compiled list of the Q&As within a few days, along with the notification that the webinar recording is available for replay on fluor.com. If you have any questions, please feel free to email the address on this slide and someone from our team will get back to you. From all of us on the Innovation Builders team, thanks and have a safe day.